I started talking about how the even indexed roots affect the absolute values. And so we're going to focus on this part again. We have two different parts, right? Whether the index is even or odd. So I want to focus on what happens when we're dealing with an even index. And I'm just going to use square roots for this, okay, but it's any even index. Okay, so there's basically kind of three rules that you need to apply after you identify that it's an even index. Okay, so again, that's the first step. Okay, so if it's an even index, and then you look into the individual bases inside the individual variables. Okay, so if you have any even powered variable, okay, so if you have an even-powered variable, you're going to check for absolute values. You're going to test the negatives. Okay, so these ones, you're testing it independently. Okay, so if we look at this first example right here, the square root of x squared. We have an even index. We have only an even power, but any even powers we need to test. So when we simplify this, it simplifies to an x. When we test it for a negative, am I guaranteed that this x will never be a negative without an absolute value? No. I need to have an absolute value. Now that guarantees it's never a negative. And so that is the simplified form. If we jump down here to x to the fourth, what's the simplified form of that? X squared with nothing left in the radical. And so when I look at this and test for the negative, because it's an even power inside that even index, I need to test it. A negative squared becomes a positive, so do I need absolute values around this in order to ensure this number is never a negative? No, I can leave it just as it is. And then when we look at this final example here, x to the sixth, what does that simplify to? X to the third. So now when I test it, if that's a negative to an odd power, it would be a negative without that absolute value. So again, I need that absolute value to ensure this is no longer a negative. And so that is the rule regarding the testing. Okay, so let's see what happens if you're testing, though, for multiple variables that are even. Okay, so if we're looking to simplify this, okay, we simplify the x, or the x's, we can remove one x with no x's left inside. For the y's, we can remove one y with no y's left inside. So this is your simplified form. We have to test these independently. So when we go back in and test this, we're just testing the x's by itself. If x were a negative, are we guaranteed that that expression will never be a negative value without the absolute values? No. So you need absolute values around your x, and that's going to make that portion of it positive. And now we can test the y independently. Does the y need absolute values to guarantee it's never a negative? Yeah. So what we can do is we can put absolute values around both of them combined, and that guarantees you're dealing with positives. Okay, what if we did, what if we did x to the fourth, y to the sixth? Okay, I want you to try that one on your own. See if you can simplify what that would be, please. So how many groups of 2x's can we remove from 4? 2. How many groups of 2y's can we remove from 6? 3. So here's our simplified form. So now when we test it for negatives, we test independently. Looking at the x's, if we take a negative and square it, that becomes positive. So do we need absolute values around the x? No. But the y, when we test it, a negative to an odd power is still negative. So do we need absolute values around the y? Yeah. And so that would be your simplified form for that. All right, so that is your first rule. Okay, any individual base variables with a power that's even, inside that even index, you have to check it independent of the others to see does it need absolute values. Okay, next, let's test what happens if there's one odd power. If all you have is if you have one odd power, you don't need to even check it. Okay, so like when we look at this one right here, x cubed, okay, there's only one odd power. So when I test this, I can remove one group of 2, leaving one x inside. And the reason I don't even need to test it is, can my x even be a negative number? No, because a negative inside a radical without something that's there to cancel it out can't be a negative, so we don't even need to test that possibility. We can see from the simplified form that you can't even plug in a negative value for x. Okay? What about this next example, x to the 5th? It simplifies to x squared with 1x left inside. Can x even be a negative? Same reason. Okay? And that's always going to happen if you only have one power of x that is negative. Okay? Which means what happens if you have one even and one are not negative but odd? What if you have one odd power and one even power? Okay? So what if you're looking at x to the 6th, y to the 5th? Okay? So if we look to simplify that, the first rule applies for the even, right? You are going to test the even powers independent. Okay, but the odd powers you don't even need to test. So when I simplify this, I can take out 3 x's, I can take out 2 y's, and I'm left with 1 y inside. Okay, when I test for my x's, a negative cubed, do I need absolute values around that to ensure it's never a negative? Yes. And do I even need to test the y's? No, because there was only one odd power, you don't need to test that one, only the even powers. Okay? Now, that brings up the final situation, and that is, what if they're both odd? Okay, these ones are going to be dependent on each other. Okay, you're not testing them independently, you're testing them together. Okay, so if you take an example that looks like this, x cubed, y cubed, and you simplify it, how many groups of 2 can you remove from the powers of x? 1, with 1 x left inside. How many groups of 2 can you remove from the powers of y? 1 with 1 left inside. Okay, so you simplify it as you would all of them. Okay, and then because your original powers were both odd numbers inside that even index, you have to test them dependent on each other. So you're testing all of them negative at the same time. You're not doing it individually, and you're testing them all at the same time. So inside my radical, a negative times a negative cancels. Outside, a negative times a negative cancels. So do I need absolute values to ensure this product will never be negative? No. The signs take care of themselves in that regard. Okay, what if I did this? Okay. The square root of x to the 5th, y to the 3rd. I want you to see if you can simplify that. Test for absolute values and see if you can determine what the simplified form would be, including absolute value symbols. So remember, these rules are only if you have an even index. So any cube roots you don't even need to worry about, right? Odd index is always going to be that top rule. The index and power cancel, leaving just the base itself, whether it's positive or negative. Okay, but when you have an even index, you do have to check. So how many groups of 2 can I remove from the powers of x? 2 with 1x left inside. And how many groups of 2 can I remove from the powers of y? 1 with 1y left inside. So there's my simplified form. Because they were both odd, I do need to test them dependent all together. Oops. Okay, so here I'm going to test my simplified form all together. So inside my radical, a negative times a negative. Those take care of themselves. Outside, my x squared, if that's a negative and I square it, the sign will take care of itself for the x's, but what about the y's? Doesn't, so I need absolute values around the y. That would be the only way I can ensure that that's never going to give me a negative value. Okay? So that is sort of the gist of how those will be tested and the rules for that. Okay? All right, so let's take a few examples of these, and I want you to try on your own. So if we look at this first example, we notice it's an even index radical, so we have to consider absolute values. Okay, both of the powers are odd numbers, which means they are dependent on each other, so I'm going to need to test them all together. So if I first simplify what I have, what perfect square factor can you remove from 18? 9 times 2, so the square root of 9 comes out as a 3, and the 2 stays inside the radical. How many groups of the index 2 can I remove from the powers of x? I can remove 2 with 1 left over, and how many groups of 2 can I remove from the powers of y? 4 with 1 left over. So here when I test these, I need to test all of them, both the x's and y's, together as being negatives. So here I have inside my radical, a negative times a negative. The signs take care of themselves. On the outside, x squared takes care of itself. Y to the 4th takes care of itself. So do I need any absolute values at all for that one? None at all. Hey, let's look at or try the problem right below that, please. That one has 2 even powers. Okay, so anytime you see an even one, you treat each even power independently. So you're going to test each one by itself. Okay, but see if you can simplify that, please. So here if I simplify numerically, I can remove a perfect square factor of 16. Now you might have to break that down, right, and remove 4 the first time through and then remove another 4 if that's the case. But here I can take out root 16 times root 7. So the root 16 comes out as a root 4 and the 7 stays in the radical. For my x's, I can remove how many groups of 2? Just 1 with no x's left inside. And for my y's, I can remove 3 groups of 2 with nothing left inside. And so now I can test, and when I test these, I test them independently. So I test the x's by themselves first. If x is a negative value, the only way I guarantee my answer is never negative is absolute values around that x. I then do the same thing with my y. A negative cubed is still negative, so I also need absolute values around the y. So I can put it around everything. Now those signs are balanced out, and I have my simplified form. So here are the absolute values around both the x and y. Okay, and I want you to try the last example right below that. There's the case where it's 1 even and 1 odd. Okay, so I want you to try simplifying that, please. All right, so when I look at this, again, even index means you have to consider absolute values. I have 1 even, 1 odd, so I'm going to test for the even. I don't need to worry about the odd. So when I simplify what I have, 150, there's a perfect square factor you can remove from that. That is 25 times 6. So root 25 comes out as a 5. The root 6 stays inside the radical. From the x's, I can remove 2 groups of x's with 1 remaining inside the radical. And in my denominator for the y's, I can remove 3 groups of 2 from the y's with nothing left inside. So these are my expressions. Because my original power of x was negative or odd, I don't even need to worry about testing x's, and it shows, right? Can x even be a negative number? No, you can't take a square root of a negative, and there's nothing in there to cancel that out. So I test the y independently. If y is a negative, do I need absolute values around it to ensure it's never going to be? Yes, I do. And so there would be my solution. Okay, so I'm just going to really quickly go through these last three here just to explain them. Okay, but they have the same kind of balance, right? One both even, one both odd, and one of each. Okay, so here 54 has a common factor, or a perfect square factor of 9 times 6. Square root of 9 comes out as a 3, 6 stays inside. I can remove 2 groups of x and 3 groups of y with no x's and y's inside. Because my original powers were even, I need to test them independent of each other. So testing the x's, a negative squared becomes a positive. The signs take care of itself. But for the y's, if that's a negative to an odd power, the signs do not take care of themselves. So I would need absolute values around the y cubed in order to ensure it's never a negative. For 175, again, if I look, this is the factors 25 times 7. Root 25 comes out as a 5. 7 is going to stay inside the radical. I have one group of 2 x's with 1 x remaining. I have 4 groups of 2 y's with 1 y remaining. Because my original powers were both odd, that's my last rule, which means I do need to check them all dependent on each other. So I'm checking all the x's and y's negative at the same time. Inside my radical, those will cancel, so I'm fine there. Outside, I have a negative, a y to the fourth gives me a negative to a fourth, becomes a positive, so no absolute values needed around the y's. But the x is a negative. Without the absolute values, you can't ensure that will never be a negative, so you do need absolute values there. And then the final example here, again, one of each. The 18 is 9 times 2. Square root of 9 comes out as a 3 with a root 2 left over. I can remove 2 x's with 1 x left over, and in the denominator, a y squared. I remove 2 groups of 2 with nothing left inside. So here, because of my odd power, my x's, I don't even need to test. Okay? And I can see that in the simplified form. If x was a negative, I get a negative inside an even index radical, which can't happen. So x can't even be a negative. Don't need to worry about that. But the y, when I test it, a y squared, the sign takes care of itself. So no absolute value symbols necessary. It's going to take care of itself.